Right, well, good morning, everybody. Like I just said, we're going to press on because it's quite a larger set of slides today, and I do have some sort of demos for you. So the topic for this session is about platform, and what I generally mean by platform is enabling sort of developers to ship new features sort of safely at speed into production. So increasing release cadence. In a sort of safe manner, so we're not destabilizing the production environment. And this heavily overlaps with the introduction of Kubernetes as well as a tool, as an orchestration platform for containers. And I've got a few little demos in here as well, sort of to go through. So firstly, I just want to start with what is a platform. Like I said, this is about as formal a definition as I can come up with for it. It's a composition and integration of a set of processes, tools, and components to build a coherent solution with the goal of empowering developers to be able to build, ship, and operate their business logic. So this is slightly detached from what you might be used to in a sort of typical environment where you've got a development team and an ops team, and the ops team are throw your code over the wall, and the ops team deploy that code and operate it. We're sort of slightly flipping that on its head in the sense that we're empowering engineers to sort of build and own their own systems, run them in production, give them visibility into what's going on, and ways to improve the operation of the system. And why we want to do this? So goals of a platform are to sort of increase productivity. One of the main things that you find as sort of teams grow and release cadences increase, so you go from releasing sort of quarterly to monthly to bi-weekly or even weekly, you end up creating bottlenecks in the operations team. So this is usually around multiple deployments. An ops engineer's got to stop, perform the deployment, all the other activities around that. Reduced toil. So what I define as toil is sort of the kind of work that is sort of repetitive, could be automated, tactical, and sort of devoid of any actual sort of business value. So again, this sort of relates closely to the scenario I just described, where you've got teams or engineering teams start to release code more frequently because the business requires a faster release cadence. What you will eventually find that an engineer or an ops engineer, who's responsible for deployments, will eventually just spend a lot of their time building environments, deploying to those environments, and promoting new versions of code to production. That basically becomes their day job, and a lot of that can actually be sort of automated away in a reliable manner. So I think that's a really good example of toil, because it isn't actually creating any value within a team, within the business. It's just something that sort of has to be done, if you like. And like I said, part of the reason why you engineer platforms, or it's become more popular now in the cloud, is because businesses want to be able to scale, and it's those economies of scale that create new problems, problems that we didn't have sort of 10, 15 years ago, because there wasn't a need to ship new features faster to customers. So a nice way of looking at this is when you're thinking about sort of scalability, is that one sort of, let's call them an infrastructure engineer, or DevOps engineer, or platform engineer, somebody like that, somebody that's working on the other side, but not on the development side. They can probably facilitate requests from maybe teams of up to between 5 and 10 developers quite happily. As long as those requests are fairly infrequent, they can manage that. But that's the limit. If you start to scale up your development teams or your engineer and the features you're building, quite quickly they're going to become a bottleneck. When we think about platforms, what we're actually thinking about is having something or tooling to support potentially hundreds and even up to 1,000 engineers. When you think about organizations running at the sort of scale of Netflix, they have thousands of engineers releasing potentially hundreds of times a day, and the only way they can do that is by having a scalable platform. So We also want the platform to be sort of cost effective, because again, we're not just here to sort of spend money on your infrastructure. Cost effectiveness for me works two ways. It's the efficient use of the resources within your cloud. That's making sure that your applications are sort of safely but densely packed onto as fewer sort of servers as possible that make sense for the type of application that you're developing. But also, like you say, utilizing and because you're reducing that toil, you're actually giving time back effectively to your other engineers to do more productive sort of business driven or business focused work. So it sort of works two ways. There's a systems cost, and there's an actual real tangible human cost attached to platforms as well. So again, slightly related to the first point, in increased productivity, platforms are generally self-service. So rather than people queuing up at the ops guy's door to build them an environment or provision some new infrastructure or deploy some code to this environment, they support the tooling for the sort of the empowerment of the developers to effectively do it themselves. For spinning up an environment is something that is not beyond the realms of the capability. It's quick. It's mostly automated. It's just amounts to sort of creating a ticket, if you like. That ticket's being serviced automatically, and when it's done, the environment's up, then it'll inform the engineer that it's there, and they can start deploying code to it. It's also quite opinionated. So, I've got a great diagram, which I won't show to you today, but it will show you the sort of where the cloud has gone to in the last sort of five years, and all the different tooling options that they all operate in the same space, but there's a lot of choice. And a good platform is opinionated about this. It's making these decisions for you so that you don't have to make them effectively. They might not always be the perfect decision. That's true, but sometimes I think that having an opinion and narrowing the choices can be a good thing, because it sort of prevents that sort of cognitive load of trying to decide and evaluate all the different monitoring tools that are example that you could use. I think there'll be reasons why we use them, but it just takes out a bit of that churn away from organizations who are thinking about adopting platforms and moving to the cloud. And lastly, I think the one thing I think is probably one of the most important things here is that a platform is collaborative. It's not just when you're talking about a fully immersive sort of platform as a service that provided by a third party. They've built their APIs. You're going to adopt their APIs. But when you've got the opportunity to sort of do it yourself and bring your own platform internally, you can be a little bit more collaborative with your engineering teams, because you can tailor it for the sorts of workloads that you're going to be running on it. So say in the case of you guys, you're running a lot of Tomcat applications, so you can tailor the tooling, and you can still be opinionated, but it's tailored around tools tools you're familiar with, and things that are going to complement the stack that you're actually running, on the platform. So this is what a sort of typical division of responsibility looks like if you think within a platform. So what you got at the bottom of this diagram here is you've got sort of your cloud provider, which again is to some degree abstracted from you, other than sort of provisioning the sort of base resources. The platform itself is supporting a lot of common operational concerns, and it abstracts a lot of that away from the developer. So the developer just really has to focus around the aspects of delivering an application into production. So it's the deployment aspect, the release aspects, the alerting and monitoring and metrics, and what emerges from this sort of architecture is sort of two primary roles within a platform. So firstly, you've got the operators. So the operators can build and maintain the platform. And these are some of the things that you expect the operators to do. They build or deploy tooling to allow developers to quickly build and test their own applications without any need for an operations engineer. They provide a service catalog to safely install approved application and services. So if you think about a use case for this, it might be that you decide to use Postgres database. You don't, in a sort of development environment, you don't necessarily need to use RDS, because RDS is expensive and it's good for production workloads that need to be highly available. But you might decide to deploy a lightweight Postgres installation into your platform that teams can use for their own purposes, for sort of development and test purposes, where you don't necessarily need the high availability components that those managed services provide you. You've got a container registry, so that's obviously allows developers to store new application versions somewhere within the cloud, and they can then pull those application versions at an appropriate time. And logging and tracing, so this just allows developers to operate their applications in real time. So, you know, a platform isn't really a platform if you can just deploy some code to it and it runs. But if you've got no visibility and insight into how it's running, you know, looking at, again, from a Java perspective, looking at the JVM, you know, looking at the sort of heap settings that you've configured and looking for memory leaks, without that visibility, it's not really a platform, because, you know, the guys that are actually deploying these workloads can't actually operate the applications in sort of real time. And the other side of the coin is that you've got developers. So developers build, test, and deploy software to the platform. So the things that they're concerned about: release management. So a platform will enable developers to decide how they want to release software. So whether they want to automatically release it to production after running some automated tests, or whether they want to have a manual quality gate before and an approval process before they release it to production, and even down to the sort of the type of deployment strategy they want to implement. You know, and I've got a session around deployment strategies sort of later on in the workshop. But, you know, deciding between doing a sort of rolling upgrade where you slowly release a new version of your application to your users, or if you want to have a blue-green scenario where you spin up a completely new environment and flip the traffic over when you're happy with the testing that you've done. They also are concerned about monitoring metrics. So, you know, as an operator, I'll say myself, I don't know much about your application. I don't know what are the important metrics that the application has, and obviously those metrics feed into how that sort of service is or how you measure the performance of that service in a sort of traditional ITIL world, if you like. You know, you want to define your service level objectives and your KPIs to see how your application is performing. Without monitoring metrics, that's not really possible. They're also concerned around alerting. So again, giving the developers the agency to decide what signals matter. You know, not always do you want to alert for everything, depending on the type of application it is. High memory in a in-memory database is something that's to be expected. High memory in a stateless web service is something that's not to be expected. So, you know, the developers know they know their software better than say operators do. And finally, sort of dashboard. So again, all these things are good. Being able to capture metrics, being able to alert on those metrics. You know, we are visual beings. Being able to view and look across a period of time to see how to make judgments is obviously something that's very beneficial to us. It's hard to sort of mine that or come to those assumptions or conclusions from just raw data. So having dashboards available to us in order to obviously measure, evaluate, and improve the service as well is sort of critical. So when I talk about an MVP here now, what I'm really meaning is a sort of minimal viable platform. So what really makes up a minimal viable, whether you buy it off the shelf from some third party or bring your own platform, these are the sort of main components of, if you like, that would constitute a minimal viable platform. So you've got your sort of CI/CD tool. So obviously CI would target your development process and how you integrate and test changes to make sure that your next release is going to be successful. Your CD tool is around getting those changes or shipping those changes into production according to your requirements, and you can use any tool you want for this. So, you know, in the proof of concept, I use GitHub. GitLab or Jenkins is equally viable. If you go to a full hosted PaaS where you're not bringing your own, they'll usually or almost always will have their own way of building and deploying your changes, so that will sort of be built into the platform. You've got your image registry. So again, you know, some people will be familiar with Docker Hub, which is a public image registry, or Quay. They're the two sort of main ones. And if you're building and publishing your own Docker images, then you can use a private registry such as AWS ECR. You've got your networking infrastructure, because cloud platforms don't happen without cloud resources. So this really constitutes your sort of your network, your subnets, your security groups. So everything we sort of covered, you would use Terraform for effectively. On top of that, then you've got your sort of container orchestration engine tool. So a long time ago, so going back maybe sort of seven or 8 years ago, when managed Kubernetes and things like that weren't a thing, there was tools called kops and kubeadmin, which basically built and provisioned clusters on various cloud providers using Ansible as a sort of configuration management tool. They're still there. These are still active projects, but obviously a lot of people now leverage the cloud providers' own versions of these tools, because it takes a lot of the complexity away from the engineers. So on top of that, then you've got your compute resources. So again, depending on where you're deploying your platform, if you're in your own data center, you might deploy it onto bare metal. If you're in AWS, you've got two deployment options. You're either going to run your containers within on EC2 within an auto scaling group, or you're going to run them within AWS Fargate, where you don't have to manage any EC2 instances at all. And something we've talked about previously, where those two options are viable, but Fargate is generally suited for where you've got sort of a stateless microservice architecture, where absolutely there's no state stored, because those containers can be discarded and replaced at any given point in time, and that's what they're designed for. But it is a very cheap option. It's good for background tasks that can potentially fail and be retried, because you're paying absolutely nothing for the underlying infrastructure. Then you've got a load balancer, so you've got something sitting in front of your platform. So this is basically routing traffic from the internet. And again, depending on where you deploy your platform, if it's bare metal or AWS, you're going to have some form of a load balancer where you can route traffic to the containers running inside. You're going to have an ingress controller. So this is something that we'll talk about in the service discovery workshop. But it's basically acting as a routing layer to coordinate how to load balance traffic across your workloads. And then you pretty much always, if you're deploying services on the public internet, you're going to have TLS termination, and the general practice is you terminate it as close to the edge of your network as possible. And again, you've got a couple of options there. You might decide to bring your own certificate authority or use a public certificate authority, or you might use Let's Encrypt, which can give you free wildcards, SSL certificates, and auto renew them really easily. So I'm going to give you a very, very quick demo before we start to get into Kubernetes itself, into the individual. I just want to give you a flavor of what a platform might look like, and whether this is Rancher is an open source sort of platform tool that sits on top of Kubernetes to help you manage your Kubernetes cluster or multiple clusters. And what I've done here is I've just set up a very simple local environment using a lightweight distribution of Kubernetes that will run on my local machine, and I've deployed Rancher to it. And I'm just going to give you a little twirl around the UI quickly before we dive into the more interesting things. So if you do use a tool like Rancher, there are a couple of other open source tools out there, or if you go to a fully hosted platform as a service like OpenShift, you're almost guaranteed to be presented with something like this, which allows you to visualize your cluster. So in this case, this is a dashboard. It's showing how many resources are deployed to my local cluster. It's showing me the Kubernetes version it's running. It's also showing me the number of nodes that I have for running containers on, and it shows me the number of deployments that are already currently running within this cluster. And it's also scraping a lot of data around the nodes. So obviously this is a local machine. So what it's actually doing, I've got a couple of virtualized nodes that are running on my machine. And it's showing the capacity as well, the maximum number of containers that I can actually run on this local environment. So at the minute, I'm only sort of at 10% capacity, which means I've got plenty of headroom. The amount of CPU and memory that the workloads deployed within the cluster are using, and a lot of events. So within the background, we talked about the control plane a couple of sessions ago. The Kubernetes control plane is always responding to events and recording those events. So those events can be propagated, and you can search those events to see exactly what's going on within your cluster at any sort of given point in time. at that point, you're free to do a number of things. I mean, Rancher in particular, you can go and have a look at any applications that have been deployed. You can go and install you can go and install applications from approved third-party repositories. So if we're just trying to think of something, so we've got Postgres in here. I mean, we might not. No, we don't. So this would be as simple as just clicking on one of these, entering your configuration details and deploying it, and that would give you say a monitoring stack within a certain within your cluster. So this is something that's a very common feature in most of these hosted platforms, and something you would expect whether you're sort of bringing your own or you're paying for it. You can actually see every single resource type that, say, Kubernetes offers. I'm not going to go through all of them because we haven't really explained a lot of them yet. But you basically can click around, look at everything that's in your cluster. You can perform operation tasks in here. You can even exec to a shell environment where you can actually work with your cluster if you want. So it's got some nice little features in here. And obviously you can view and then most other platforms as a service will have users and authentication baked into it. So you could integrate your SAML environment or Google or anything like that to provide your user access and authorization levels. And a lot of these platforms as a service now also support sort of continuous delivery as sort of native to the platform itself. So they'll have a way to, so obviously at the minute, there's nothing in here, but you could create a Git repository pointed to a repository with some Kubernetes manifests in, and anytime that repository is updated, it would automatically deploy them into the cluster. But that's a sort of an advanced topic, and we'll cover that another time. So before we just jump into the actual looking at the sort of primitives within Kubernetes, what I just want to do is just briefly explain what we're going to cover. The documentation is obviously really, really good. It's sort of full API documentation. It's kept up to date. It shows you the differences between versions of the API resources. The main sort of API resources these days very, very rarely change. They're very stable, so you can sort of rely on them. Some of the more experimental ones do get promoted from time to time from sort of alpha to beta to sort of official stable, but they're very good at communicating those in the wider world. So these are the resources that basically give us the focus for the rest of the session. We've got the pod, which is the smallest unit of scheduling within a Kubernetes cluster. A pod, in its simple terms, is a number of containers. It can be 1, it can be 10. Generally speaking, those containers are very closely related together. In most cases, they tend to be 1 container, to be honest with you. You don't tend to deploy many containers into a single pod, because that sort of defeats the purpose of having that level of control. You've got a deployment, which is a management controller for pods. So this is a control loop that is constantly evaluating the state of the running pods and reconciling those changes if something, say if a pod crashes, for example, for whatever reason, it runs out of memory, it would be replaced to maintain the state of your application deployment. You've got service. So, again, consider the scenario where you've got pods running all over the shop. You don't necessarily know which actual physical or virtual machines these pods are running on at any given time, but you need a way to access them and load balance across them. So a service is an abstraction which creates a virtual IP, which maintains a list of the IP addresses of all the pods across a fleet of machines. So if you send any traffic to that service, it can effectively load balance to all the containers and all the pods that sort of sit behind it really effectively. You've got a config map. So pods usually are running applications. Applications need configuration. A config map is basically a resource that can be attached to a running pod and provide it with configuration. So if it's environment variables, or if it's a properties, Java properties file, that sort of encodes and handles all the mounting for you. So again, that's sort of abstracted from the developer, and it sort of in the secret is basically a more sensitive version of a config map where you can't actually get the values encoded into a secret out of your system without a little bit of extra work. So it's obviously it's a good way of storing the sort of API tokens, usernames, and passwords, and things like that. So if you try and view those resources, the actual data itself is encrypted. However, from the pod's perspective, it gets to see the unencrypted version. So, you know, if you want to put man database credentials in, you would use a secret. You've got logs, so obviously no different. We haven't talked about any logging framework here. Ultimately, containers write their logs to standard out, and the container engine actually manages the logs for you, and you can view those logs. You've got a exec keyword, which is basically allows us to do some troubleshooting because we can actually access the running pods. And then we've got port forwarding, which enables you to sort of tunnel to your containers from anywhere, so outside of the cluster environment. So what we're going to do now is we're going to start. I'll attach a quick time check. Yeah, we're looking good for time. Going to take you through just a number of demos and just show you all these primitives and how they work in practice. So what I said before, a pod schedules a group of related containers to the cluster. This is a very simple manifest for a pod. So you can see we've got the API version. It's v1 because it's stable. It's one of the first things that were created many moons ago. The resource type is a pod, you know, as is the name. We've got some metadata associated with that pod, so we've given it a name so we can identify it within the cluster. And then we've provided a specification. So in this case, it's made up of one container. I've given it the name of the container. I've given it the name of a public image. So this is just an image called HTTP bin. Some of you guys might be familiar with the website HTTP bin, which allows you to call and get almost like an echo server for REST APIs. I'll show you how it works in a minute. And I've defined the port as well that it runs on. So notice here that the port that it runs on is actually port 80. You can run your containers on whatever port you like. There's no restrictions on needing to have sort of pseudo privileges to run on ports less than 1024. You can literally pick whatever container port. And the way the networking works is that you can run other pods on the same port and it has no effect effectively. So that's quite nice. You haven't got to worry about what ports you actually want to run and worry about port conflicts in these environments. So I'm just going to take you through to here with a bit of luck. So just going to tree that. Just going to show you the pod YAML. So exactly the same of what's in the slide there. We're going to use kube control, which is their command line 2, and the apply keyword and the file parameter, and we're going to give it with a bit of luck, we get a response from the API server that says it's created the pod. We can use kube control then to get the running pods in the current namespace, and you can see the status of it is container created. So it's in the process of obviously deploying that container to one of the nodes within my local cluster. And it's up and running. And that's it. And again, if I delete the pod, it's gone. So that was the simplest version of you deploying something to your cluster, having it running, and then tearing it down afterwards. So interestingly here, when I deleted the pod, it stays deleted. And obviously I've talked a little bit about it maintains the availability of your containers that are running in the cluster. And that's because the pod is sort of the smallest unit, and you don't typically deploy pods, you deploy deployments, which manages a group of pods in sort of concert. So that'll be the sort of next thing we look at. So here we have the deployment. So this is the sort of resource that you would usually interact with, and it manages a pod specification to ensure availability. So that's what we have here. It's slightly different, but fairly similar in other ways. You'll see there you've got a different API version because it's a different group of resources. There's a different kind because again it's a different resource. You've got some additional metadata where we're applying some labels to the deployment. So these are just key value pairs that mean something to your organization. So I've given it a label of app and HTTP, so I can identify it through kube control. And then some of the differences here in the specification. So you can see there's a new attribute called replicas. That means we're going to run 3 versions of this service of this pod. The selector So the selector is actually going to match. So the deployment needs to know about which pods it needs to manage, and we tend to match on labels. So you apply labels to the pod, and then you select those labels in the deployment. So if you can see, we've got match labels here. We're matching the app label, and the app label has a value of HTTP bin. So any containers that spin up with a label app equals HTTP bin is going to be managed by this deployment controller. And this actually provides you, it might seem quite trivial on the face of it, but it provides you a huge amount of flexibility in how you want to organize your cluster effectively. The template attribute is basically the pod specification that we saw in the previous example here. So if you notice there that you've got an array of containers and you list the containers and container ports, it's almost exactly the same here. The template, everything within the pod template is covered under the the deployment template here. So if we fire out back into our next example, so we have a look here, we've got the deployment. It matches what's in the slide. Apply that to the cluster, and we just view the pods that have been spun up. You can see that we're creating, or in the process of creating, three exact pods running the exact same container. You'll notice in the name of the pod that the deployment name is suffixed with a sort of a hash, if you like, of the container. So that's to just ensure that the resource names are unique within a given namespace. And what's interesting now is if I try and delete one of the pods, so let's just say delete this one, for example. So what this is going to do is actually kill the container running on one of the nodes, or wherever this node is running. You can see that almost automatically the deployment, and it's very fast as well, almost automatically the deployment manager has seen that there is no longer 3 replicas of this pod running, and it's replaced it almost instantaneously. And this can be really beneficial, you know, if for whatever reason one of your pods crashes, runs into a sort of a state that's sort of unrecoverable and can be discarded. If your application can start quite quickly, then you know you almost never lose the capacity within your to service traffic within your application. And just because probably nice to show you something, there's a describe keyword within, or describe job within the kube control, so you can actually look at the specifics of the pod if you really want to, and this applies to any resource. But just sort of gives you a flavor of what sort of information that the cluster actually maintains about your application. So you can see it's got some of a lot of the information that we supplied within the specification, like the labels. It gives you the IP address that's been assigned to it by the control plane. It gives you information about the container, such as the hash and the version and things like that, and the hosts you've exported. It gives you some conditions, you know, around the state of that container. So in this case, it's been initialized, it's gone through all the states, it's up and running, and it's healthy. And then you've got some events. So again, you know, because everything is event driven in here, it's always recording what's happening. You've got events about what happened. So there's an additional, so the scheduler has basically assigned this particular pod to run on this particular server. It's got to pull the Docker image down. It's successfully pulled that image in sort of less than a second. It's created the container and it started it up. And this is the same for any single resource within Kubernetes. You can describe it. It's got metadata. It's got event data around it. So you get you can always see what's going on and what the brain, if you like, the control plane is actually doing, even though you're not necessarily responsible for all this. You've got the ability to do it. So let me just tidy up here. Cool. So the next resource I want to just show you is the service. So if you recall what we said earlier, by default, you've got pods aren't accessible outside or even inside the cluster at this point. You've got pods get assigned IP addresses, and you potentially could deploy something into the pod into the cluster and resolve that IP address and speak specifically to that pod, but in practice, that's not something you really want to do. You want to spin up a fleet of pods and you want to load balance traffic between them. And you don't really care where those pods are running. That's the whole point. So what the service effectively does is creates a virtual IP address. And again, similar to how the deployment works, it uses a selector, a label selector, to target the pods that it's going to manage the endpoints for, or the pod IP addresses. And if you hit and then what happens when you create a service is that it will create a DNS entry as well. So the control plane comes with its own DNS server, the implementation of which is up to you, whoever, usually it's called core DNS. It creates an apex zone for the cluster on the domain service.cluster.local. And when you create a service, you can reach any pod that's deployed that is backed by that service just by using the internal DNS mechanism on port, in this case, port 8080. So you notice you can actually expose your service on a completely different port from the container port, which is again quite powerful. You don't run into sort of port conflicts and things like that. So what we'll do now is we'll take that deployment that we've just seen, we'll put a service in front of it, and I'll just show you how you can sort of talk to that service effectively. So again, just to show you very quickly, we've got the same deployment as before. We're going to deploy 3 versions of this HTTP Docker image. We're going to run it on port 80, and we're going to give it the label app HTTP. Then what we're going to do is we're going to put service in front of it. So the service is of type cluster IP. So this is Kubernetes is about 3 types of service. I'll cover them all in detail in another session. But basically, cluster IP means it's registered with internal DNS. It's not accessible outside the cluster. So I couldn't access it from my local machine, if that makes sense, because I've got a couple of virtualized machines running on this machine that are equivalent to my EC2 instances. The containers are running on those instances, but I cannot access them from my host machine effectively. And in this case, there would be the wider world or the internet. So what we'll do is we'll just deploy the service. We can describe the service. And you'll see here again, just we've been given the IP address currently. So this is the IP address of the service, not the IP address of the pod, and this is the IP address that would be registered with DNS. And just give it a second. What we should see is that the ports should get recognized with it. Spare me a second. Lost my notes. So let me just check. Oh, that'll be why I didn't deploy the. We've got our 3 pods created. And there we go. That's what we're missing. So we've got our virtual IP that's been assigned with DNS, and then we've got the endpoints, which are the pod IPs that are being managed for us. So anytime those pods get destroyed or recreated or moved to another node, the pod IP is going to change because they're going to be allocated from a different CEDAR block. The kubelet on the control plane will manage that for you. We'll update the service. We'll update DNS. So whenever you hit this IP address, you're going to hit one of the pods that are actually running somewhere within your cluster. And what we can do here is just to demonstrate this is I'm going to deploy a single-use container, should we call it, something that is not running a process like a web server. It's just going to create a shell running inside the cluster that I can curl and demonstrate that this service is accessible to you guys. So what we're going to do is we're going to spin up a Docker image. So this is just a Docker image that's got curl in it, and we're going to deploy it to the current the current cluster. The namespace, and in a second, there we go. That gives us a shell. So now we're actually inside a container with a shell terminal using the TTY, and we can run curl commands within it. So what I can do is I can curl the service on the following URL. So if you remember, we've deployed it on port 8080, so we're going to use port 8080 of that. And the HTTP Docker image basically creates an API where I can return whatever HTTP status code I want. So in this case, if I said I wanted to return a 201, if I call that URL, it's going to return a 201 created HTTP status code. Yeah, and if I change it to 404, so it's just a little tool that just enables me to interact with an actual real API, and you can visually see something's going on in the background. So just one word of or point of notice is that the default word here, this is actually the default, the name of the namespace. So when you spin up a new Kubernetes cluster, your local configuration points to a default namespace. All these demos are being deployed to this default namespace. So when you come to actually using the internal DNS, you just prefix it with the name of the namespace that you're trying to reach. So if I deploy this into a namespace A, then default would get replaced with A, or namespace B, it would get replaced with B. This bit, however, is specific to your cluster, and it's global effectively to your cluster. So just think about this as a sort of domain delegation to the default namespace and the service running within that namespace, and you can reach anything you want. Let's exit that. So you can see that everything's still running. So I'm just going to tidy this up. Oops. And we should be empty. So when the curl sets down. So now we've got our pods, we've got a way to manage them, and we've got a way to sort of expose them to the cluster. Pretty much always you're going to want to configure those pods. Depending on what they're doing. If they're a Java application, you're going to want to inject some application.properties for the environment. And this is where the sort of config map and the secrets resources are used. So basically, they inject configuration data into your applications. So you can see I've used a slightly different sort of syntax for this code block because this is just YAML. If you want to delineate different resources, you can just use these 3 lines and apply. When you do a kubectl apply, it will create both of these resources sequentially. So what I've done here is I've created a config map, a very basic config map, and I've encoded some data in here. So every item under the data attribute is a key value pair. This can be something as simple as a string, or it's completely free form, or it could even be a full configuration file, which I'll show you an example of that in a minute. I'm going to create a pod as well, and that pod is all it's going to do. It's going to be a pod that runs one time, so it's not running a background process. It's going to start up, it's going to execute this command, and then it's going to shut down, but it's going to stay in a stopped state effectively. It's not a background process, so it's not continuously running. It's not listening on a port. It's going to execute and then shut itself down. I'm just going to echo the environment. And the reason for this is that we're using this additional keyword under the pod specification to basically say, I want to populate my environment using this config map. And what it'll do is it'll export these key value pairs as environment variables within the pod. And this is going to show you what that actually looks like. So again, just do a bit of a tree. We've got two scenarios here. We're going to map something to an environment variable, and then we're going to map it to a file. So that's usually the more useful one. Let's have a look at the value ones here. So as you can see, we've got config map, and we've given the config map a name, so we can refer to it within the cluster. We've created some data associated with that config map, and then we're deploying a pod that's going to use and mount those values into the environment. So you can see there, it's slightly different from the previous examples because it's not a background process that we're running like a web server. We're just running a bash command with a BusyBox, very lightweight Docker container. It's run the command, it's finished. The status of the container is complete because it did an error or it exited with a 0 return code. and it's obviously not ready anymore because it can't receive any traffic. However, what we can do is we can introspect the logs from this container, or the output, and you'll see that these are all the environment variables that were populated when the container was executed. Now, obviously, there's some that are populated by Kubernetes. Anything that's prefixed with Kubernetes is managed by them. However, you will also see that we've got our custom environment variable here that's been populated. And you can refer to those environment variables then in your startup scripts or your application, however you want to use them. But as I said, typically this tends to not be that useful once you start to deal with application workloads and you've got potentially hundreds of configuration items. You're typically want to put those in a file. So I've got another. Let me just delete that one a second. We've got another version of using a config map and mounting a file into the container instead and reading from the file. So the syntax is very slightly different. So here we're creating a new config map and we're creating a key, which is the file name. And we're also using the multi-line YAML syntax to allow us to actually define something a bit more free form. So in this case, it's a JSON object with bar equals bars. But this could be an application properties file. It can be whatever format file that you like. The pod's definition is almost exactly the same, apart from the fact that we've changed the command. So in this case, we're trying to read from a file. So we expect that file to be mounted into the container when it starts. And we're going to assume that it's mounted at /op/bar.json. And the only other thing that changes then is there's a new keyword introduced here where we define a volume, which creates a Docker volume that gets attached to the container. So this is a bind mounted volume. So it only exists for the period that the sort of container exists for, and it's sort of torn down and destroyed afterwards. And within this other keyword where we can control how we want to mount this volume, which refers to this config map, into the container. So in this case, what we're going to be doing, we're saying, well, we're referring to the bar conf volume. We want to mount it at /op/bar.json. And because we want to mount just a specific attribute or data element in the config, we're going to give it a subpath element, which is bar.json, which refers to the key here. So if you had multiple key pairs, so if you wanted to store all your environment config in one place, you might have bar test, bar dev, bar prod, and have 3 different sets of config there. This allows you to refer to individual keys, so it doesn't try and mount all of them into a single environment. And the result of this then, volume, so exactly the same. It will create the scenario as a previous example. It's run the container, hopefully successfully, because the status is completed. So that file must have existed, otherwise it would have returned a non-zero error code. And if we got the logs for that container, we'll see that all I've done is I've echoed the contents of that file. So this just demonstrates, I say, the flexibility you want and how you want to get data that doesn't exist with your app into your sort of environment, and generally speaking, this is used for application configuration more often than not. This is a very basic way of doing it. There are more advanced ways of doing it where you might integrate it with a cloud provider's sort of backing service. So if you so in AWS, they have a managed service called Parameter Store, and that could store your JSON file, for example, and it's fully managed and versioned, and it can be, and from that JSON file, you could, as part of your deployment, you would automatically create the config map on the fly, whereas I've defined it sort of statically. You can make it dynamic by using these tools. But like anything, you start simple. When you outgrow it, you look for better solutions or sort of fit what you're doing. So next, we're going to look at secrets. So secrets are, well, as they say on the tin, they're meant to obfuscate and sensitive information from people using the cluster, whether that's humans or even other workloads. So, if you had your production database credentials encoded in a secret for a specific container, What you wouldn't want to do is have everything within that cluster be able to read those secrets, because that's a potentially security risk. It sort of goes against having strong access controls and granting least privilege. Secrets enable you to basically, enforce some good practices or security practices within your cluster. So interestingly here, the difference is I've not created, if you like, a manifest, because it would make no sense in that case. I'm going to just show you how to create these from the command line, and I've got two different types of secrets. Okay, just to tell you the two different things you can do with the kubectl command line. I'm going to create a secret containing a public and private key from files that I've already created. And I'm also then just going to create a secret from a literal string. So if I wanted to create some secrets for some API tokens, for example, I can use these commands and it'll create them for us. And then I'm going to show you how to just decode those secrets so you can read them back in plain text. So just have a look here. We've got the public key and the private key that I created earlier. So you can create a secret containing as many keys as you want and you can mix and match for both as well. So you could, in theory, have a number of from file arguments and a number of from literal arguments. And you'll see how they're created in a minute. So you can see that the secret was created. Again, referring to a new resource, I can get secrets that are in the current namespace. So you can see here I've got one called SSH keys, and there's two data elements in there, which one for the public key and one for the private key. I can describe those secrets. So interestingly here, because what you can't see is the actual content of those secrets, it just shows you the size of them, because this, what we wouldn't want to do is leak the private key and public key out to people that don't need that information, or other containers that are inside the cluster running that don't need that information either. However, it should be noted that they are only base 64 encoded. So you can actually decode them yourself, provided you've got the necessary authorization to do that. And you do that through the right, hang on, let me find the right one. Ooh. There we go. Spare me a second, guys. So obviously what you've got is all the resources are just YAML by default, but what you can do, if you're familiar with JSON pathing, you can grab attributes from the resource out and do stuff with them. So in this case, I'm interested in the data resource, the SSH public key. Make sure I put that in the right. Oh. So you can see that's the base 64 encoded value of the public key. And if I want to just pipe that through base 64 decode, I get my public key back. So you can decode them, obviously, provided you've got the requisite access. And the same can be done from the other secret. So if we just create the other secret, the API tokens, list the secrets out. So we've got a new secret resource being created. Again, it's got two items in there, which will be the two API tokens that I've created. And again, we can just use the same command to basically decode those secrets. So what did I call them? API tokens. Again, using the same JSON pathing structure. What was it called for? Token 1, I think it was called. So again, you've got a token there that's base 64 encoded. Type it through base 64 decoding, and there's my secret foo again. So again, this is typically what you'd use for storing your database credentials. within these sorts of platforms, and this is how they'll be sort of stored at rest. As your requirements become more complex, you can integrate third-party, like I say, sequence providers such as AWS Sequence Manager or HashiCorp Vault. But generally speaking, they require some complexity to set up and some expertise to operate effectively. So I always recommend just starting with what's simple first, and I'm making it more complex when you need it. Try and reduce that complexity when you're just starting out with using sort of Kubernetes. And then I just wanted to just talk a couple of minutes about how we would sort of troubleshoot in these environments. So it's all well and good, like I say, being able to deploy things into the cluster. But say we talked about how important sort of visibility is into what's going on. Obviously, the most obvious thing for us to deal with is logs. So by default, most of your containers won't use a login framework, or if they do use a login framework, they'll be configured to write a standard out rather than your typical file, because the container engine manages that for you. So it's one less thing, if you like, for developers to concern themselves with. So those container logs will be written on the node, and you can query the API to introspect those logs. So what we'll do here, we're just going to jump up into the troubleshooting here. I'm going to put the HTTP deployment back on. Use the log command, grab the pod. And as you can see there, I can view the logs for that particular pod. So this is just, I think this is just, I think it's a Python, it's just a Python process, I think it is. Yeah, using Giga. So what it's doing is it's spinning up a web server on port 80. There's not a lot going on here, but get your point. If you've got an application that's got actual logs that mean things, then you can easily see them. What is worth noting is that at the minute, if you're introspecting logs, you introspect logs at a sort of at a pod level. In these sorts of environments, you would do centralized logging, and you'd pull all these logs off these servers and push them to a central store. But that's again for a future session. And lastly, I want to be able to just show you a couple of other things that you can do. So you can actually exec into the pods, provided they ship with a shell. So in this case, we can basically control exec into the pods. Myself. So the syntax changed recently, so I need to remind myself. TTY. There we go. So you can see my my shell's now changed, and I'm now in the pod as the root user, because the process or the user ID of the process that's running is root or PID1, and it also shows the name of the pod that I'm in. So if I just, no different to being in a Unix environment now, I can run things like PS and grab a list of all the processes that are running. So you can see PID1 within the container is running the here's Python 3 server. So it's running this process, and then it's obviously spawned a worker to actually deal with the requests here. I can do, and I can move around the file system as if it was I was just on any other operating system, if that was the case. All Unix commands work is no different to me being on my sort of host machine. So again, that's useful for sort of debugging things like there's some special folders that might get mounted into these containers, for example, that mounts tokens. So you can go to these directories, and you can see some things that the control plane has actually mounted into the tokens into the pods themselves to allow you to do things like to allow them to participate in role-based access control. But again, I'll cover that in another sort of session. And lastly, I just want to show you that you can actually forward to a specific pod. So when I talk about, it's not something you generally do unless you were debugging an individual pod. You generally go through the service, which load balances across a fleet of pods. You can use the port forward command with a host port and the container port, and then you can actually get traffic onto that. So in this case, if we did kubectl port forward pods, we're going to map it from let's call it 9999 to port 80, Yeah, and you can see there now with any traffic that we on our local machine that hits port 999 is going to get forwarded to this particular pod on port 80. And if we just spin up another terminal, I should be able to curl localhost 999 status 201. There we go. So I'm getting the 201 response from the pods, getting the 404 response. So I've got full connectivity to that container that's running. So I am a little bit conscious of time. I thought we were going to run a little bit later today, so I'm going to try and get to these last few bits a little bit faster. So on the other side of the coin, we've talked about having what are the sorts of things that a developer would be exposed to. Well, all these resources that we've just been through are the ones that they'll be familiar with, at least at a high level. On the other side of the coin, we've got the operators, and typically what are the things that they deal with. So they deal with the node, which is the physical resources available to the cluster, whether that's EC2, AWS, bare metal, and managing the sort of resource quotas that are assigned to the various applications that are running. They deal with namespaces, which is the sort of logical isolation of sort of workloads within a cluster, which we'll go into in a second. They deal with a special namespace called kubesystem, which is the namespace containing all the data plane and the control plane. So if we just have a look here. Oh, sorry, I'm on the wrong terminal. So as you can see here, this particular cluster is running a bunch of sort of services that the developer wouldn't be necessarily aware of, but they're providing the important parts, if you like the DNS pod, for example. They're all typically deployed into their own namespace and sort of protected by role-based access control, so you can't accidentally give access to the wrong peoples. And the operators would also be familiar with a tool like Helm, which again we've got a separate sort of session on, as a means of sort of installing additional tools into the cluster in a sort of managed way. So tools that they haven't necessarily written, like a Postgres database or a blog or something like that, where they just want to tweak a few knobs and dials and the various settings on it and just deploy it straight in the cluster without having to manage anything, and it's there available for anybody to use. So we've got the nodes here. So this is just a simple output from kubectl get nodes. So if we just go back here a second. So this lists my nodes, but if I describe the node or specific node, I can get all the information from it. Yeah. So that's all that is. And some of the key elements on here, it's sort of showing how much resource it's got to allocate. So in this case, this particular VM's got 6 CPUs. How much ephemeral storage is attached, so there's 50 gigabytes. How much memory, 16 gig, and what's the maximum number of pods based on what the control that this particular machine or node could run. So 110, it's quite a few. Considering it's my local environment, that's quite a few pods. It shows you exactly what is deployed to this particular node and in what namespace it's running. So you'll see there there's a metric server running on this particular node that's at the minute not consuming any resources. But in the case of where I've done an earlier deployment, it was also running the HTTP container within it. And it's also got some events for you to look at. So whenever the node maybe becomes under pressure for memory, CPU, disk, all that information is here, and generally speaking, that's constantly updated because it's a little controller that's running and always checking the health of your node, make sure that it can accept new pods. And obviously, if it can't, that would flag up, and you would provision a new node effectively to cut that slack. So a little note on namespaces, because they will become important in some of the future lessons. So namespaces provide a mechanism for isolating groups of resources within a single cluster. So if you take your example or your environment, for example, you've got 100 customers. What you want to do is deploy the same application with the same name into a single namespace for 100 customers, because you would basically get some collisions on resources and a name and resources. And it wouldn't be the best way to do it, because ultimately all the traffic within the namespace is completely completely transparent. So customer A could talk to customer B just by knowing the pod ID. So that there's a security element there as well. Generally speaking, what you would do is create a namespace per customer, deploy your applications into that namespace and then isolate those namespaces from each other using a network policy, which is just a set of sort of whitelisting, or blacklisting address spaces within the cluster. So just good to know that obviously the names need to be unique within a namespace, but not within across namespaces. And I think I've got just a little example here I can show you. Just make sure there's nothing running in here a second. Oops. Yeah, so what I've got here is I've got a little application made up of a deployment. So it's going to run one HTTP bin container and a service. And what I'm going to do, so what else we got there? I've also created 2 namespaces, so one called A and one called B. I'm just going to create the namespaces first. You can see that the 2 new namespaces have been created there at the bottom, A and B. I'm going to apply the application into namespace A, and I'm going to apply it into B as well. So you notice now that if I do kube control get pods, apart from that one, those applications are no longer running in the default namespace because I've specifically told it which namespace I want these applications to be deployed on. They've gone into a different namespace. So if I want to get access to them and view them, I can just give the -n parameter and A, and you can see there's the namespace. And likewise in B, the namespace. So they share exactly the same deployment name, but because they're scoped to a separate namespace, they don't get they don't collide on the naming resources. And if you remember earlier when we talked about services, so we did get the service in namespace A and the service in namespace B. So they've got 2 completely different virtual IPs, and those virtual IPs will be backed by a number of endpoints, which reflect the pods that are currently running. They're running on exactly the same port. And within the internal DNS records, you'd be able to access on 2 completely different URLs. So it'd be http://a.service.cluster.local or http://bin.b.service.cluster.local. So it's very predictable. When you deploy a workload into cluster, accessing that particular service becomes very predictable. You haven't got to work out where it is. You can usually work it out from the topology of the way you've deployed it. The kube system namespace, so again, I've just showed you very briefly, it's a sort of a reserved namespace. The main reason it's reserved is because a lot of the containers that run in this namespace actually have host privileges. And one thing we try and prevent is when you deploy applications, or your applications, you wouldn't necessarily give them root permissions. They wouldn't run as root, and they wouldn't have permissions to access the host infrastructure as well. This is just purely for sort of security reasons. However, there are some elements of the control plane that need to access the host with elevated privileges, like sudo, for example, because they need to manage things like IP tables. They need to manage different configurations and network interfaces and things like that. So it's just really important to remember that everything that runs in kube system is high risk, high privilege, and should be secured. Everything outside, we should strive to not allow it to run with elevated privileges that it probably doesn't need. If you're asking for elevated privileges for your application, usually there are better ways to design your application to not require that and keep it good. Keep the security levels sort of acceptable. And just to finish up, I just want to cover a couple of advanced topics here that obviously we haven't got sort of time to cover today. So you've got sort of init containers. So init containers, if we just go back to our pod example, maybe. Pod cycle. So an init container, it would be a container that runs to completion before your actual container starts up. So these are, so where you've got in specification here containers, you would have specification init containers, and you would list all the containers, and they run sequentially. So if you define 10 of them, the first one will run, if it exits with a 0 return code, the next one will run, and so forth until all of them are finished. If all of them are finished and they all exited with a 0 return code, then your actual application would start. And this is really useful for doing things like loading configuration in from, say, third-party sources, standing up a database schema, bootstrapping the system in some way. So, if you were running like a Kafka cluster or something like that, you might just want to advertise, do some advertising or set some parameters ready for discovery. It's a common pattern you'll see in these environments that are used to sort of their benefit. Jobs. So jobs are a bit like what we saw with the config map containers. So if you just going for config maps. So the job, again, it's got its own resource type. So the kind would be a job instead of a pod, but effectively it would work very similar to how the pod works here, in that the container runs once to completion, performs a task, and then sort of disappears. I don't find a lot of use of them, to be fair, but it's just one of those core resources that it's good to have some visibility of. Daemon sets are a very special type of deployment. So a daemon set is a deployment where the control plane will guarantee that one instance of your container will run on every single node. These are very good for things like, oops, excuse me, I don't know why we went over there. These are very good for things like exporting system level metrics or node level metrics, for example. So if you imagine you want to ship your system statistics to CloudWatch, then you need to have this process running on every single EC2 instance that you're running, and daemon sets facilitate that sort of behavior, because it makes guarantees about how many of those there will be, and it will always keep one on every machine alive, compared to deployments where you can have as many as you like and there's no guarantee they will run on a specific node. Stateful sets are basically deployments for use for applications that provide state. So an obvious example of that is a database. A database has sort of identity. A database needs to have storage attached to it, and that storage needs to be where that container is going to be deployed. And stateful sets are going to say good for that sort of thing, because they have identity. So when we talk about pods and deployments, they have no identity. They just get a random hash assigned to them, and they run anywhere. Stateful sets, when you spin them up, so let's say I wanted a Kafka cluster and I want a 3-broker cluster. If I deployed it into Kubernetes, every pod would have an ordinal ID so you'd have broker 1, broker 2, broker 3. And each of those brokers would be deployed on a very specific node, which would have the storage provision for it on that node. And this is so you've got some reliability around the behavior then. So, because for example, what you couldn't do is move broker 1 from one node to another node, because the data volume wouldn't be there and it would probably bring down the cluster. So it gives you some guarantees around the state of these services. Again, I'm a big fan of not using them unless it's absolutely necessary. I think databases sit better outside of the cluster, but I think there are some limited use cases, for example, development databases and stuff where you can use stateful sets quite successfully, or small things like blogs that require a database that you can back up. And lastly, you heard me mention it a couple of times that Kubernetes supports a full role-based access control API, so you can define what resources and what verbs any particular actor within this system can perform, whether it's a user or a container, by using RBAC. And it's enabled by default within cloud providers, and generally it starts with least privilege. So by default, nothing's got access to anything. You open up you open up the gates to what services and what parts of the API that you want to have access to. So again, just enforcing some good sort of security practice from the out. And that's it, guys. Like I said, went over a little bit. Got maybe 5-10 minutes for questions if anybody has any.
Anna, I have few.
Yep.
So first of all, there were two kind of specifications. One is labels, and another one was match labels.
Yeah, deployments. So let's just fire. I'll just go straight into code for this. So let's go back to this. Yeah,
Yes.
yeah.
So what is the difference between these two?
So when we talk about the metadata attribute on a resource, right, this is applied directly to this resource. So a name,
Okay.
because we need to identify it, and the labels, like I say, there we go. I've got some nice IDE integration there. Labels allow us to project whatever we want onto the platform. You know, whether it's
Okay.
an application, you want to put like application or a tier, so front end, back end, or customer, you know, customer A, customer B. That's what labels affords us. It gives you the flexibility to project your organizational structure and your topology onto the resources, and then make decisions. So make decisions based on that topology. So in this case,
Okay.
we've given
So it's like it's a kind of app. If we say that it kinds of customer, it's like kind of the port that this specification is for.
yeah. So in the case of a deployment, a deployment needs to monitor a number of pods that are run to be able to make decisions about when to stop and start or scale up or scale down. So obviously, it on its own, you know, without the selector, it wouldn't know what pods to match. So what we do is
Okay.
we apply the label to the pod, we
Okay.
apply a label to the deployment. You don't actually need this. This is more for sort of completeness, because generally you would do.
Yes.
So this is probably the simplest definition of this. So as part of the deployment specification, we're saying that we want this deployment to watch any pods match with these matching labels. So it's going
Okay.
to look to see where they're running in the system, and it's going to monitor them. And this is how we tie the two things together, because they're two separate resources. I suppose you could think of them as a bit like a referential integrity in a database, if that makes sense.
Okay.
But the nice thing is, because it's so flexible, you can do some really cool things. I mean, not just with deployments, but other resource types which also support these types of selectors. So if you look at the other example we had with services, and I can show you what you can do with them in another one. So services work in a very similar way. This is basically saying, well, we want to create a virtual IP. So again, this is not actually needed here, but it's more belt and braces, like sort of standard practice. This is not actually needed. What we're saying here is we want to create a virtual IP. We want to map this service port to this container port, and we want to direct the traffic. So we're looking for the endpoints. Again, we're looking for the pods to route the traffic with, because the service manages the virtual IP, not the number of pods. It's got a single responsibility, and we're just selecting based on the label that's applied to the pod, and that's how it sort of ties them both together. If I change this, then effectively the service wouldn't go anywhere, because it wouldn't be able to identify any pods. And the nice thing you can do with this is, in the future, I've got a really good example to show this. I could add multiple labels. So let's say I had version V1, for example, and then I decided to deploy version V2. I could update the label, and then automatically it would flip the traffic from pointing to the pods for V1 to the pods for V2. So you could almost create a blue-green deployment scenario, but just by using labels.
Okay.
Anything else?
Yeah. So next thing is we discussed about the secrets in Kubernetes.
Yep.
And you mentioned that there is a command to access the secrets as well. So how can we access? Is there a way to access those secrets in our code, like Java or Spring Boot somewhere?
Yes. Yeah. So I haven't actually got an example in here, but basically it's exactly the same as how the config map is. It's just slightly, obviously, it's a different attributes. So let's say we've got. So here, I think you can actually map. My autocomplete is going to work. I think it's secret map, if I remember correctly, off the top of my head. But basically, the syntax is what the specification is almost exactly the same. In fact, it's just that you're reading from a different resource. So in here, you're reading from a config map. There, you're reading from a secret map. And as long as the the terminology, if it was the same, if this was a secret, it would work. So yeah, they're basically the same thing. The only difference being is that it doesn't show you what the contents of that secret through the command line unless you have the privileges to basically decode it.
Okay, but how can we access this secret map in our Spring Boot code? Because ultimately we would need these secrets in our code, like API tokens and everything.
Yeah. So this is where you've got that contract, if you like. So if you mounted the secret as an environmental variable and went into that container, you could just do env and you'd be able to see it plain text within there. Likewise, if you mount it as the secret as a volume, you can open the file, you can view the contents of it. So that's in the container. That's within the same user space as your Java process is running. So in that case, what you would typically do, so if you're using Spring Boot, for example, I think Spring Boot automatically can grab environment variables, so straight from the environment and map them to beans. Yeah, so you could have a Spring Bean that defines your application configuration that's populated entirely from environment variables. And when you deploy your code, if you mount your secrets as environment variables,
it will work in a similar way that you have shown this config map volume.
Yeah,
so
almost identically to this. Yeah. So there's with Spring Boot, it's great because it's designed that way, and there's very little. You don't have to write your own configuration loader. It basically will do two things. You either use a Spring profile if you're mounting from a file, or multiple Spring profiles. Excuse me, I was whinging about that. Or you would just mount it from, or map it from, use the property mapper to map it from an environment variable. So you've got complete flexibility of how you want to pull those in at that point.
Okay. And this storage, the config maps and config maps that we discussed that this is a temporary storage for all Dockers, right? All containers. So whenever the container is down, the storage related to will also get down, right?
So the config map will always be there, so you haven't got to worry about that. So the nice thing is that config map can be used and referred to by any instance of your container. So if you've got five EC2 instances and you're running three pods on three of those out of five, that config map is accessible by all of them. And if, let's say, one of your pods crashed and got spun up on a different machine, it's already there for it to pull from. So there's actually no need for anybody to say, oh, I need to put the secrets or the application config over here. It's already there.
Okay, so where does that Kubernetes puts those config maps? Because that's accessible for all of our containers. So when will it be down, or when will it be deleted from our Kubernetes nodes or everything?
So it would only be deleted if you removed it. So typically speaking, when you do your deployment, you'd have the config map there already for the environment you deploy into. And obviously, if you ever deleted that deployment, then it would remove the corresponding config map. But what you can also, because you're using namespaces,
yes,
if you've got, say, application 1 running in namespace A and application 2 running in namespace B, the application in namespace B couldn't look up the secrets from namespace A. It can from a network point of view, it can contact, by default, it can contact the application, but it couldn't actually access the secrets or the config map from a different namespace. So that's where the namespaces start to become really useful in sort of safeguarding your resources.
Okay, so these config maps are not temporary then, it's a permanent kind of storage as well.
Yeah, they are and they aren't, because they're not backed by sort of EBS, if you like.
Okay.
They're sort of the Docker volumes, so they're sort of temporary volumes that are sort of created when the container is spun up, and when the container disappears, those volumes are destroyed if they're no longer needed. But that's part of the control plane that sort of manages that for you. You can obviously mount persistent storage to your.
So unless we have any one container running, those will be accessible to us, the config maps. Like Till when, till then, the config maps will be accessible to us whenever there is any single container running that
Yeah,
is
yeah,
executed.
you can read. Yes, of course, again, you can read from them whenever you like, as long as as long as they're deployed, they're there. So you can deploy the config map without the container and just view the config map. You can deploy the container to use the config map. You can remove the container and leave the config map there. It's completely up to you, but as long as the resource still exists within the cluster, then you can obviously access it.
Okay. Okay. So, like in our case, we have the properties file, and that is, suppose we are using the Dockers.
Yeah,
So we have the property files, and we have kept it on the base machine itself, and we have mounted that drive on into the Docker.
yeah.
Okay. And how will that work with our config maps, those properties?
So what if we go back to this? Probably this is the best example I can give you with the volume. So to take this for example, if this was a Java application, we would define a config map called, let's call it application test for argument's sake. Properties. So in here you would have, let's imagine we're just doing the Spring Boot app. So we've got server.ports.
Yeah. And can this be picked up from file as well, or we need to have it like key value pair here?
It can be picked up. So there's a couple of ways you can do it. So you can either obviously manually create the config map, yeah, and
Okay.
manually update it and then redeploy it. You could put that configuration within, say, a backing store such as parameter AWS SSM parameter store, and it would
Yeah.
automatically create the config
Create a
map.
config map for
Yeah,
us.
on the fly. Yeah. So this is very much the simplest version of it, where I create a config file. I might have I might have 3 of these in here. So that's, staging, and that's production. And in my sort of production deployments, then obviously I would mount the application product properties instead. Let's see, we just see. So it'd be like application properties.prod. And then obviously within your Spring Boot application, if you want, what you could do is if you mounted that particular file to your resources directory, yeah, or somewhere on the class path, then you can just use a Spring profile with application prod, or a Spring profile prod active would automatically pick this property file up, wouldn't it?
Okay.
So there's a whole way, there's a whole raft of ways you can do it. It obviously very much depends on what, how you're doing it. What I try to encourage is that, in some environments where you've potentially got multiple programming languages, try and keep a consistent configuration interface. So whether if you've already got Spring Boot, I try and encourage people who use like Node.js or Go to use similar mechanisms for populating application configuration, because it just gives you some consistency across your environment. But obviously, if you're just using sort of Java and properties files, then it's sort of a one size fits all solution anyway.
Yeah. Okay. And somewhere we discussed about these kube system that are our system ports that is automatically run by
Yeah, this one here.
Kubernetes.
Yeah.
And we discussed about that we need to secure it as well.
So
Like secure the access of because they have the host privileges like that, right?
yeah. So by default, I mean, by default, these have got host privileges. Whoever's sort of let's say the cluster operator would have access to these, because they understand those components. They wouldn't be something that the developer would need to ever get involved with. Developers wouldn't be allowed to deploy things into this namespace, because it's sort of reserved. So that would be a sort of restriction on what they can do, which is just a sensible restriction. Other containers that are running in other namespaces, again, don't by default have access, but what you would do is just deploy a network policy that sort of basically prevents any ingress from any of your customer namespaces from accessing any of these services by accident. So it's not that difficult to secure it, but obviously it's just good to be mindful that this thing exists and that they obviously have access to the host machine in sort of a fuller capacity, which you don't usually afford to your application workloads. So it's no different to say you wouldn't run if you're on an EC2 instance, you wouldn't run your Tomcat server as root, for example, because obviously it gives it far more privileges than it needs to run. You would probably run it as a specific application user called Tomcat. So it's no different to this at that sort of level.
Okay, sure. And the next thing I think we have already discussed that we can share the config maps among ports as well, right? The config map that we have deployed, we can share it among different ports unless it is in the same namespace.
Yeah. So you could have one, say if you had 4 or 5 different applications running in one namespace, you could have one config map that that has the configs for all, or you can have one per application. Again, it's complete flexibility, and it depends on really how you build and release your applications.
Yeah, sure.
But obviously, obviously, I'm in a position to advise once because obviously I haven't had much exposure to your actual applications. It's very difficult to say. I can only sort of say what I recommend best practice would be. But generally speaking, once you've had an eyeball of the code and the applications, it's a lot easier to make those sort of determinations of what works best for you, whether to store it as a single config map for the entire environment or multiple config maps for one for each application.
Yeah. So that's all. That were my questions.
I have a question. Like this, we discussed about this configuration map. Is there any provision to modify these maps on the fly?
Yeah, so there is by default if you edit a config map. So again, kubectl has absolutely wrong window. kubectl has. Let me just deploy this a second again, very quickly. So we've got the config map. You can use kubectl to edit things directly. I mean, it's not recommended because obviously it's out of band with your automation, but I'm just showing that you can do it. Obviously, it will open it up in whatever your favorite editor is. So I could go in and just change that to oops. Oh, what are you doing? Change that to foo. Shows it's edited. I can describe the config map just to show that change is being persisted. Yeah, so you can see the change. However, if I try to read the value from that config map now through in the pod, it would pick up the original value. So, however, so what you can do is you can force it to pick up the new changes, right, by restarting. Or basically delete the pod. If you delete the pod, the deployment controller would provision a new one. The new pod that comes up would pick up the new value. So that's one way you can do it. But obviously that's a bit of a brute force mechanism, if you like. Other ways you can do it is you can provide an annotation on the deployment that says if the config map's hash value, so ever changes, then redeploy or restart the pods to pick up the changes. So that's another way you could do it, which is I've got a demonstration of sort of that in the next session. However, again, sometimes you might want to be able to reconfigure your applications on the fly without bringing the pods down. And for that, then you'd use something like Spring Cloud Server, which can pick up, which is dynamic enough to pick up configuration changes from a source, and this source would be the config map in this case. And apply those changes to the running Java process. So that's a more advanced use case. But so I would only recommend that again if you really need it. It depends on how you're currently working. But again, I can show you that when we come into doing a few more advanced topics.
Sure.
Cool. Any more? No? Okay. Well, sorry guys, I had a feeling that one was going to run over because there's a lot more to get through. So tomorrow we're going to look at sort of deployments and how you'd realistically how you would manage deploying into your cluster with Helm as a first sort of protocol. And show you some different methods of doing that and what it looks like and what the sort of developer experience is. So I think we've got the same time slot, sort of 7 a.m.
So just a second, Dana. So if everyone is okay, and if Dana, if you are okay, can we keep that session today evening as well?
Sorry?
If that's not, can we keep that session for today evening, like around 6:30 our time?
I'm
Helm
sorry,
session?
I've got a full calendar today. I'm afraid I've sort of booked them in for 7 to 8 UK time for the rest of the week. Can you just let me know if that's not
Yeah,
suitable?
actually from next week I'm not available. I've my marriage is there, so
Oh, you get married? Congratulations.
yeah, thanks. So
Uh,
from next week onwards, I'm not available. So I'm trying to cover up all this session in this week.
okay,
And we have a holiday on 26th as well.
hang on.